Hello everyone, in this video we'll be looking at section 9.10, which is Taylor and Maclaurin series. So in the previous section, what did we look at? We said if we could rewrite a function so that it looked like a over 1 minus r, then we could use the geometric series formula to rewrite it as a r to the n, and therefore we could rewrite that function as a series, right? But in general, not every function can be written as a over 1 minus r. So if a function can't be written as a over 1 minus r, then we have to use that idea that we looked at in the section before, which is Taylor and Maclaurin polynomials, right? Taylor and Maclaurin polynomials, remember, gave us a nice approximating polynomial for a given function, right? So we're going to take that idea and now look at that polynomial, that Taylor-Maclaurin polynomial as a series, which means an infinite sum, and then that sum will then be our series for some of these functions. Right? So subsection 1 here, Taylor and Maclaurin series. In this section, we will study a general procedure for deriving the power series for a function that has derivatives of all orders. Right? So as long as a function has derivative of all orders, then we're able to write its Taylor series. So theorem 9.22, the form of a convergent power series. If f is represented by a power series that looks like the infinite sum of a sub n times x minus c to the m for all x in an open interval containing c, meaning that, remember, it converges on this interval around c, then a sub n has to look like the nth derivative at c over n factorial, and the general and the formula for f of x has to be this infinite sum. And this infinite sum, remember, is just the Taylor polynomial centered at c, but going on infinitely forever, right? So that's why it's called a Taylor series. So what does this mean? This means that if a power series converges to f of x, then the series must be a Taylor series. What it does not say is that every series formed by the Taylor coefficients will converge to f of x. Right? So if I had a general function and I found its Taylor series, then that doesn't necessarily mean that the Taylor series converges to f of x, right? But in this section, we're not really going to look at when Taylor series converge necessarily. That's not what we're going to focus on in this class, but that's just something to keep in mind, right? Just because we create and find this Taylor series, we don't necessarily know that it converges to our function. We would have to show that it converges to our function. But again, that's out of our pay grade. Okay, so the definition of a Taylor-Maclaurin series. It's exactly this series right here is what we're going to say. Right? In other words, it's a Taylor polynomial that is infinitely many powers of x, right? It's adding up infinitely many terms. So if a function has derivatives of all orders at x equals to c, then the series that looks like the sum of the nth derivative at c over n factorial times x minus c to the nth is called the Taylor series for f at c. And if c is equal to 0, then it's called the Maclaurin series. So oftentimes what's going to happen in this section is a question is going to give us a function and it's going to ask us to find the Taylor series for that function. So what are we going to do? We need to find, if we're asked to find the Taylor series, then we're asked to find this, right? In order to find this, we need to find the nth derivative over n factorial plugged in at c. And so, and then we need to find a general formula. So what we're going to do is differentiate f with respect to x several times and evaluate that derivative at c, much like we did with the Taylor polynomial case. And then we try to recognize some pattern in these numbers, right, when we plug the derivative in at c. And then we use the sequence developed in the first step, right, all those powers to find our Taylor coefficients and find a formula for our Taylor series. Whoops. And this, I actually screwed up. Let's get a new one here. Sorry about, whoops, wrong one. There we go. Okay, so Use the definition of Maclaurin series to find the Maclaurin series for f of x equals sine x. So again, the Maclaurin series we know in general is going to look like the sum from n equals to 0 of f prime, where we're centered at 0 over n factorial x to the n, again because we're centered at n. So in order to figure out what a formula for this, we need to look at the first few derivatives, right? So, and we need to look at the function all with 0 plugged into it, right? So f of x is equal to sine x, f prime of x is equal to cosine of x, f double prime of x is equal to negative sine x, f triple prime of x is equal to negative cosine of x. And then f to the fourth derivative of x is positive sine x, right? So in other words, remember after the third derivative with sine and cosine, we know that it repeats, right? And just for fun, let's do the fifth derivative as well, which would be cosine of x. So again, we know that after the third derivative, this guy repeats. So we'll have a pattern for writing infinitely many terms. Okay, and then what do we need for the formula? We need to plug in 0 at all these points, right? Or all these functions. So f of 0 is sine at 0. Sine at 0 is 0. F prime at 0 is cosine of 0, but cosine of 0 is 1. F double prime at 0 is negative sine at 0. Sine at 0 is 0, so this is 0. F triple prime at 0 is equal to negative 1. The fourth derivative at 0 is equal to 0. And the fifth derivative at 0 is equal to positive 1. So again, this pattern will repeat after the first four terms or after the third derivative. Okay, so again, I'm trying to find this Taylor polynomial. This Taylor or Maclaurin series, right? So I'm adding up infinitely many terms. So again, what will this look like? Just writing out the first few terms, f of 0 plus f prime of 0 x squared versus x to the first power, plus f double prime at 0 over 2 factorial x squared plus f triple prime at 0 over 3 factorial x cubed, and so on. Right, so f at 0 is 0. F prime at 0 is 1 times x. F double prime at 0 is 0. F triple prime at 0 is negative 1. So this looks like negative 1 over 3 factorial x cubed. The fourth derivative is 0. The fifth looks like positive 1. So this looks like 1 over 5 factorial x to the fifth, and so on. So again, what does this look like? X minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth. And remember, this pattern would continue, right? It would repeat that every other term has a positive 1 coefficient or a negative 1 coefficient, right? So I know that since the coefficient for x to the fifth was positive, the next one's going to be negative, and it would be the next odd number, right? So this would be 1 over 7 factorial x to the seventh, plus the next one would be positive, and it would be the next odd, so 1 over 9 factorial x to the ninth, and so on. All right, that's what the pattern would look like. So now I need to create a formula for this. So this is n equals 0, this is n equals 1, n equals 2, n equals 3, n equals to 4. I like to write out n equals below each term so that way I can remember what value of n I'm using to create that coefficient there. Okay, so the sum from n equals to 0. So first we can talk about how we get the signs of each one, like whether it's positive or negative. Notice that when I plug in a negative value for n, I get a negative coefficient, right? And when I put in an odd power of n, I get a negative coefficient. and when I plug in an odd power of -1, I get negative, right? So what I'm saying there is that if I perfectly write in -1 to the nth power, that will give me the sign that I want, right? That'll mean that the odd terms, or the terms with the odd values of n will be negative, just like I need. Okay, and then now we got to think about, okay, sometimes looking at the very first term is not super helpful, but maybe looking at maybe like the third term or the fourth term is helpful because the pattern really starts to show itself. So when I plug in n equals to 2, I get 5. So in other words, and when I plug n equals to 3, I get 7. So what's the relationship between 2 and 5? Well, I multiply it by 2 to get 4, and then I add 1. What's the relationship between 3 and 7? Well, I multiply 3 by 2 and then add 1. So every time what I'm doing here is I'm taking x to the 2n plus 1. Anytime you see 2n plus 1, that's our way of saying we want only odd stuff, right? Because 2 times some number plus 1 is always going to be an odd number. And since we only have odd powers of x, that's what we're looking for there. And then notice the power of x is exactly the same as the factorial that's in the denominator. So in other words, I need 2n plus 1 factorial in the denominator. And I just make sure it worked for the first term because I wasn't looking at that term. So for n equals to 0, I get 2 times 0 plus 1, so I get x to the first power over 1 factorial, which will give me x, and life is good. So this is my formula for the Maclaurin series of signs centered at x. So again, just a little side note here, I cannot conclude that the power series converges to sine x. I just know that this power series converges to something, right? So this was a power series that I derived from looking at sine x, but I can't actually confirm that it converges to sine x unless I do a little bit more work. But again, that's a little bit above our pay grade. We're just going to be looking at finding those Taylor and Maclaurin series. Okay, so let's look at another one here. Use the definition of a Taylor series to find the Taylor series of f of x equals cosine of x centered at pi over 4. Right? Okay, so I'm just going to do the same thing that I did before. Right? I have my function is f of x equals cosine of x. So my derivative is negative sine x. My second derivative is negative cosine x. My third derivative is positive sine x. And my fourth derivative, remember I'm back where I started, and I get positive cosine of x. But we'll go ahead and write the fifth one as well, just for fun. So again, this one's going to repeat after the first 4 terms. But we write it in there anyways. Okay, and now I'm going to plug in pi over 4, right? Remember, pi over 4 is just the point radical 2 over 2 and radical 2 over 2. So all of these are just going to be either positive or negative radical 2's over 2, right? So cosine at pi over 4 is going to be radical 2 over 2. Negative sine at pi over 4. Well, sine at pi over 4 is radical 2 over 2, but then we throw a negative sign there. So this is negative radical 2 over 2. F double prime at pi over 4 is going to be negative cosine, so negative radical 2 over 2. The third derivative at pi over 4 is going to give me positive, radical 2 over 2. The fourth derivative at pi over 4 is going to give me positive radical 2 over 2. And then finally, the fifth at pi over 4 is going to give me negative radical 2 over 2. So this one's a little bit strange because notice I don't have every other sign, every other term changing sign like I did before, right? And we see the behavior a lot that every other sign or every other term changes sign, and that's where we use -1 to the n. Right? Or a -1 to the n plus 1. But here, it's going to be a little bit trickier because it's I have 2 negatives followed by 2 positives, followed by 2 negatives, followed by 2 positives. Right? Okay, so in general, what does this look like? My Taylor series looks like, let's see here, f the nth derivative of f at pi over 4 divided by n factorial x minus pi over 4 to the nth power. Right, so what does this look like? This looks like f of pi over 4 plus f prime at pi over 4. Whoops, that one doesn't need to be over anything. F prime at pi over 4, x minus pi over 4 to the first power plus f double prime at pi over 4 over 2 factorial, x minus pi over 4 squared, and so on. Right, so when we start plugging in our values over here at the right hand side, I end up getting positive radical 2 over 2 plus, now minus radical 2 over 2 x minus pi over 4. Now minus radical 2 over 2 times 1 over 2 factorial x minus pi over 4 squared. Now that we're at the third derivative, it's plus again. So I get plus radical 2 over 2, 1 over 3 factorial x minus pi over 4 cubed. Plus, now we're at the fourth derivative, so that one's going to be plus again. So square root of 2 over 2, 1 over 4 factorial x minus pi over 4 to the fourth. And now at the fifth, we're back to negative. So I get negative radical 2 over 2, 1 over 5 factorial x minus pi over 4 to the fifth, and so on. So now I got to figure out how to write a formula. So let's write everything else except for the sign, the SIGN sign of each one of these. So again, I'm starting at n equals to 0, right? So this is n equals 0, then equals 1, n equals 2 term, n equals 3 term, n equals 4 term, n equals 5 term, and so on. Okay, so first we notice that every single term has a radical 2 over 2 in it, right? So I need to make sure that's there. And then now, again, maybe starting to look at like the third term or so for n equals 2, that's where we can really start seeing this pattern. So I know that I'm always going to get 1 over n factorial times radical 2 over 2. And then I'm always going to get x minus pi over 4 to the nth power. Right? And so now I just got to figure out the signs of each one, right? And again, I would hope I could write just, negative 1 to the n, but in this case, that doesn't work, right? So notice here I have the power of n, and I'm going to write the power of n, and I'm going to write the sign, all right? So if n equals to 0, we know that it was positive. If n equals to 1, we know it was negative, and n equals 2, it's negative. N equals to 3, it's positive. 4, it's positive. 5, negative. 6 would be negative, right? And so we need a way to write the power of x that, write the what power of negative 1 we put on to get this pattern. And here's the pattern. I should write negative 1, in order to get this to happen, I should write negative 1 to the power of 1/2 times n times n plus 1, right? And you'll notice if I do that, then I end up getting the right signs, right? So for n equals to 0, it would be 1/2 times 0, so negative 1 to the 0 power is positive. Now how about when I plug in 1? Well, I do 1/2, I do 1 times 2, which would be 2 times 1/2, which would give me 1, which would make it negative. Now, the key is that we still want to have the trick about this is we still want some of the positive powers, some of the even powers to still be negative, right? So looking in the case of n equals to 2, it would be 2 times 3, which would be 6, divided by 2, which would be 3, and negative 1 to the third power gives me the negative sign that I need there, right? So kind of by trial and error, you see that that is going to be the formula that we need for the negative 1. And now we should just doctor this up a little bit so it looks more like something, a nice formula. So I'm going to write negative 1 to the 1 over 2 times to the 1/2 times n plus 1. And then I'm just going to rewrite this as radical 2 over 2 times n factorial times x minus pi over 4 to the nth power, right? Just to doctor it up a little bit, because we typically have our -1 to the power of whatever out front. And so this, like I said, at the top of your head, if you weren't able to come up for this, the power of this power, the power for the power of -1, that's okay. But now you've seen it, and now you know if you ever see this pattern where I have like 2 negatives followed by 2 positives followed by 2 negatives and so on, you need this 1/2 times n plus 1, right? So that's kind of a little bit of a trick that we learned in this problem. Right, and so this is the Taylor series centered at pi over 4 for cosine of x. All right, we'll go ahead and end this video here.